Another day, another story. In the world of deep learning, one groundbreaking framework has been making waves: Generative Adversarial Networks, or GANs. In this script, we'll delve into the essence of GANs and explore their wide-ranging applications, including their recent foray into natural language processing, NLP. At its core, GANs consist of two key players: a generative model, denoted as G, and a discriminative model, referred to as D. These models work in tandem, learning from each other in a captivating dance of creation and detection. The generative model, G, aims to capture the distribution of real-world data, whether it's the intensity of pixels in images or the sequence of words in text. On the other hand, the discriminative model, D, plays the role of an expert, trying to distinguish between real and fake data generated by G. To grasp this dynamic, think of it like a game of making counterfeit money. G is the aspiring counterfeiter, while D plays the role of the bank, striving to identify fake bills. Interestingly, D inadvertently helps G improve its counterfeiting skills as the game progresses. Mathematically speaking, we characterize real bills as X, and the features created by G from random noise as G, Z. We use a metric, J, to measure how real or fake a bill is. D's job is to lower J, G, Z, the score of a fake bill, while increasing J, X, the score of a real bill. As this cat-and-mouse game continues, the model distribution drawn by G gets closer to the real data distribution. Eventually, an equilibrium is reached, where D can't distinguish between real and fake data any better than chance. This marks the moment when G has achieved its optimal counterfeiting skills. GANs have made a significant impact in the realm of computer vision, feature representation, and more recently, in natural language processing. They've been employed in document modeling, dialogue generation, sentiment analysis, and domain adaptation, just to name a few. Now, let's explore the basic structure of GANs. In its original form, GANs consist of two neural networks: a generative model, G, and a discriminative model, D. G creates fake data from random noise, while D evaluates the quality of the data. The training process involves two objective functions. D aims to maximize its objective by becoming better at distinguishing real from fake data. Meanwhile, G tries to minimize D's objective by improving the quality of the fake data it generates. This back-and-forth training process continues until an equilibrium is reached, and G becomes an expert counterfeiter. However, the vanilla GAN isn't without its challenges. It can be tricky to train and sensitive to hyperparameters and architecture. That's where Wasserstein GAN, or WGAN, comes in. WGAN introduces the Earth Mover Distance metric, which makes training more stable. It replaces the original GAN's loss function and employs a gradient penalty technique to avoid gradient issues. Now, let's explore how GANs are making waves in natural language processing. In document modeling, GANs have shown promise in generating documents that are competitive with state-of-the-art models. They can capture complex data distributions effectively. Dialogue generation is another fascinating application. GANs are used to generate human-like responses in conversations. By using reinforcement learning, GANs can produce responses that are indistinguishable from those of humans. These applications demonstrate the incredible potential of GANs in the world of NLP. In conclusion, Generative Adversarial Networks, or GANs, are a captivating deep learning framework that has revolutionized various fields. From computer vision to natural language processing, GANs continue to push the boundaries of what's possible in artificial intelligence. As technology advances, we can only imagine the exciting possibilities that GANs will unlock in the future. Thanks for watching.